Hello and welcome to this lecture. We've studied the definition of eigenvalue, eigenvector. We've figured out how to compute eigenvalue, eigenvector. We're going to see a little bit of properties of eigenvalues, eigenvectors, simple properties. We'll go through them quickly. A few definitions of things like multiplicity and all of those things we'll do now. Okay. The first is the eigenvector independence property. It's a very powerful and useful property. Right now, also it's useful, but even otherwise it's very, very useful. Let's say you have two eigenvalues, lambda 1 and lambda 2 for an operator t, and two corresponding eigenvectors v1 and v2, and these two are not equal. Okay, lambda 1 is not equal to lambda 2. Okay, in that case, okay, v1 and v2 will be linearly independent. Okay, so notice how easy it is. If you have two unequal eigenvalues, then the corresponding eigenvectors have to be linearly independent. So, this is a very nice fact to remember. Eigenvectors of distinct eigenvalues are linearly independent. The proof is actually quite simple. I am going to quickly go through it. Let's say on the contrary, you assume not necessarily on the contrary, you just basically assume, let's say you have AB such that AV1 plus BV2 is 0. Okay, what do I have to show that the BV1 and V2 are linearly independent? If there is AB such that AV1 plus BV2 is 0, I have to show A equals 0, B equals 0. Okay, then they are linearly independent. How do I do that? I just hit it with t first, hit this equation with t. And what happens? AV1 is AT of V1. What is AT of V1? T of V1 is eigenvector with eigenvalue lambda 1. So, you get A times lambda 1 V1 plus B times lambda 2 V2 is 0. Okay. Now, I have two equations. Previously, I had only one equation. Now, this one. Now, I have another equation here. When you have two equations, what can you do? You can try and eliminate something. Okay. So, here is what I am doing. I am multiplying this first equation by lambda 2 and subtracting the second equation. So, this b lambda 2 v2 is common, it will go away. You get up a into lambda 2 minus lambda 1 v1 is 0, and from there, right, you can conclude this lambda 2 is not equal to lambda 1. So, this is non-zero, v1 is non-zero. So, the only way this becomes 0 is if a is 0. Okay. So, you get a 0. In a very similar way, you can show b is 0. So, both of these are 0. So, v1 and v2 are linearly independent. Very, very important property for a distinct eigenvalues. Okay. Now, it turns out null space and eigenvalues, eigenvectors are also connected. Okay. So, all of it is here, you can see that. So, first of all, what do I know for an operator t in R2 to R2? Rank and null and range are connected like this, right? This is a standard property, we have seen it multiple times. So, what happens is 0 is an eigenvalue of t. When is 0 an eigenvalue of t? 0 is an eigenvalue if and only if null t is not the origin alone. Okay, so this is an interesting connection, right? This is what connects rank or the nullity. Nullity and rank, are related. Nullity connects to the 0 eigenvalue. Okay, 0 is an eigenvalue if and only if the nullity is at least 1. Okay, or rank is not full, or t is singular. Okay, so that is what I've said here. If matrix is singular, one of the eigenvalues is 0. If the matrix is invertible, all eigenvalues are non-zero. Okay, so this is a very nice connection between eigenvalues and invertibility of a matrix. Okay, so the proof is given here. I don't want to go through it. It's quite simple. You can show that if null has something a non-zero vector, then that vector is an eigenvector of t with eigenvalue 0. Okay, so it's quite easy to see, right? If v is not 0 and v is a null of t, tv is 0, but 0 is also 0 times v, so 0 becomes an eigenvalue. Okay, whenever there is a null vector, 0 becomes an eigenvalue, very easy. Okay. Now, on the other way around, what is the other way around? The converse of this statement. If a non-zero eigenvector has eigenvalue 0, then clearly t times v is 0, v 0 into v, 0 into v is 0. So, this v belongs to the null space of t. Okay. Both ways it is true. So, these two are if and only if conditions. So, singular matrix can have a 0 eigenvalue, invertible matrix cannot have a 0 eigenvalue. Okay. So, this is a very nice connection between rank and eigenvalues, eigenvectors. Okay. The next property is quite easy. It's just the property of the quadratic equation. If you write this quadratic equation out, you see that you get lambda squared minus a11 plus a22. If you expand this equation out, the quadratic equation, you get lambda squared minus a11 plus a22 plus this product a11 a22 minus a12 a21. So, notice what these values are. This a11 plus a22 is the sum of the diagonal elements of the matrix. Okay, and this guy a11 a22 minus a12 a21, you might have learnt is the determinant of the 2 by 2 matrix. Okay, so the sum of the two roots lambda 1 plus lambda 2, okay, right. From this quadratic equation, it's minus b by a. So, minus b by a is just a11 plus a22, and so sum of the two eigenvalues of a 2 by 2 matrix is actually equal to sum of diagonal elements. Okay. So, the sum of diagonal elements is also called the trace of a matrix. Trace of a matrix is the sum of the diagonal elements, and that is equal to the sum of the eigenvalues. Likewise, product of the two eigenvalues just by this quadratic equation, right. In this quadratic equation, product of the two roots is this c by a, and that is just the determinant of the matrix M of t. So, product becomes the determinant, sum becomes the trace. So, this is a very important property of eigenvalues. This extends to other cases also. Okay. So, another important characterization of these eigenvalues is something called algebraic multiplicity. It's very simple. I am going to go through it very fast. When you solve for the equation, you may get two distinct real roots, in which case each of these roots have multiplicity 1 because they occur only once as the root. If you have multiplicity 2 real solution, okay, what should happen is a11 and a22 have to be equal to that solution. Okay. So, this basically, when will you have equal roots? This has to be 0, okay, this has to be 0, the right hand side has to be 0, okay, a12 or a21, one of these two have to be 0, and a11 and a22 have to be equal. Only then this quadratic equation will have equal roots, right. So, you can see that very easily from here. You can also write it down the other way around and equate the, the b square minus 4ac to 0, and you will see you will get the same conditions, okay. So, one of these a12, a21 has to be 0, and these two have to be equal, and they will become the equal eigenvalue, okay. So, in this case, you notice that this lambda 1, this a11 or a22, the equal value occurs twice as the root of this equation. So, that has got a algebraic multiplicity 2, and in this case this will also be real, right, because these are all real matrices, okay. Now, you may also get a complex conjugate solutions, okay. In this case also, lambda 1 and lambda 2 will not be equal, they are conjugates of each other. So, each lambda I has a multiplicity of 1, and this is reasonably easy to see, okay. So, these are the multiplicity of roots, how many times it occurs as a root, okay. One easy fact that you can see, sum of algebraic multiplicities, I made a spelling mistake here, I will correct it later, it is algebraic multiplicities of all distinct eigenvalues has to be 2, okay, very easy simple property for remembering. Okay. There is also something called geometric multiplicity. So, you have an eigenvalue lambda, the null space of t minus lambda I, you know, is actually not empty, it has got non-zero values or not just the origin, there is something more. So, dimension of this null space is called the geometric multiplicity of lambda, okay. So, we know that geometric multiplicity cannot be 0, right, because we know that this null t minus lambda I has at least one non-zero vector. So, dimension has to be at least 1, but it cannot be more than 2. So, geometric multiplicity is either 1 or 2, okay. Just like algebraic multiplicity for an eigenvalue was either 1 or 2, geometric multiplicity is also 1 or 2, okay. So, here are examples. We saw this example before, you had two eigenvalues, both had algebraic multiplicity 1 and geometric multiplicity 1, right. The dimension of the null space was 1 in each of these cases. When you looked at 1 1 0 0, lambda 1 is 1, there is, and it occurs with multiplicity 2, okay, right. So, this is called algebraic multiplicity 2, and geometric multiplicity is also 2. When you do minus lambda, you will get 0 0 0 0, and that null space has R2. So, dimension is 2. If you do 1 1.50, you see that lambda 1 is 1, it has got algebraic multiplicity 2, but its geometric multiplicity is 1, okay. So, when you look at, these are the only 3 cases that can happen, no, nothing else can really happen. Of course, you have the complex case, in which case algebraic multiplicity will be 1, geometric multiplicity will also be 1, okay. So, geometric multiplicity of lambda is basically number of linearly independent eigenvectors with eigenvalue lambda. So, that is geometric multiplicity, okay. So, okay. So, how do you compare, so geometric multiplicity and algebraic multiplicity? From the previous thing, we saw very clearly this is true for any eigenvalue, algebraic multiplicity is greater than or equal to geometric multiplicity. There is a proof sketch here, it is very, very simple. You can see in every single case, you have to have algebraic multiplicity being greater than or equal to geometric multiplicity. So, this is a good fact to remember, okay. So, let us summarize what are all the possibilities that can happen when you have eigenvalues and eigenvectors. So, this may have two distinct solutions, lambda 1, lambda 2, in which case m of t minus lambda I into I, for any I equals 1 or 2, you will get this matrix, and this matrix has nullity of 1, okay, and you can find the eigenvector quite easily, it is either this or this guy, okay. So, you can look at that and you will see that these belongs to the null space, right. So, if you multiply this with this matrix, you will get 0. It could be also the other one where you multiply this by this one. So, nullity 1 is very easy to understand. Or you may have one real root with multiplicity 2, in which case that real root has to be equal to both the diagonal elements, and the off diagonal elements should multiply to give you 0, right. And then in that case, m of t minus lambda 1 I will have 0 here, and then a12 here, a21 here. One of these is 0, I know, but both may be 0. If both are 0, then nullity is 2, and any basis of R2 becomes the eigenvectors, right. In linearly independent eigenvectors, or all non-zero vectors of R2 are eigenvectors. In case nullity is 1, a12 is not equal to 0 and a21 is not or a21 is not equal to 0. So, you may only get 1 0 or 0 1 as the eigenvector. So, this particular case usually is called a deficient case or something. It's as if, you know, the eigenvalues promise 2 eigenvectors, but you get only 1. Okay. In this case, you get 2 linearly independent eigenvectors. Okay. So, this sort of summarizes all that you can get with eigenvalues and eigenvectors. I urge you to practice more with those examples on your own. Make sure you quickly find eigenvalues, eigenvectors given a matrix. Okay. Thank you very much.